everyone, Mrs. Basega here, and today we're looking at our last application of Newton's second law. That is forces on ramps. Now, as you recall from our lessons drawing free body diagrams, forces on ramps include gravity, normal force, friction that prevents the solids from sliding past each other, and let's just say in this case that there's an applied force. Let's say we're moving out of our house and we're pushing a couch down a ramp. In order to draw the free body diagram, I want us to notice a few things. The normal force is perpendicular to the ramp. Friction and applied force are parallel to the surface of the ramp, but the gravitational force is straight downward. A thing to point out is it would be awfully inconvenient to have to use sine and cosine to split applied force, normal force, and friction force all up into their components. Note that would mean we're doing sine 3 times and cosine 3 times. Wouldn't it just be easier to take the one odd force out and split that one up into its components? But which one would it be? Which force is not perpendicular to all the others? To help us think about it, let's look at a problem we've done before. Originally, we had done two-dimensional motion problems by taking the applied force that was up at an angle and leaving all the other mutually perpendicular forces, friction, normal, and gravity, exactly the same. We then used sine and cosine to split up the purple applied force vector into its x component that caused acceleration, that was Fa cosine theta, and the y component that helped cancel the normal and gravitational forces, that was Fa sine theta. We were then able to take the components and use them to replace the applied force in a free body diagram. In this case, we'd see that the applied force going to the right cancels the friction force going to the left, causing a net force and acceleration to the right. We're going to use the same exact principle, but when it's on a ramp, it's more convenient to split a different force into components. You'll notice that on a ramp, 3 forces are perpendicular to each other: normal, friction, and in this case, if we're pushing an item down a ramp, also applied force. Those 3 are already perpendicular to each other. So in my coordinate system, I'm going to leave them alone. Friction should be smaller than normal force because coefficient of friction is always less than 1. I can see applied force and friction canceling each other, but what to do about this gravitational force? Well, that is a force at an angle, so I should be using sine and cosine to break it up into its parallel and perpendicular components. I'm going to call these FGX and FGY. FGX's job is going to be to pull objects down the ramp, whereas FGY's job is going to be to cancel out the normal force, just like gravity did before. The x component, on the other hand, will cause things to speed up as they travel down the ramp. FGX will cause acceleration. So let's take a look at these components a little bit more closely. Essentially, what we're doing here is we're rotating the original coordinate system. If you imagine you took an XY plane and you're just rotating it until it lines up with the system of this ramp. In this case, the positive x direction is going to represent down the ramp in the speeding up direction. The negative x direction would be up the ramp. The positive y direction would be out of the ramp. Think like floating up above the ramp, like away from the surface of the ramp. Whereas the negative y direction would be into the ramp. Imagine like sinking into the mud on the side of a muddy mountain. Now, what does the gravitational force look like in this coordinate system? We know that Fg equals mg. That stays true. However, in this new coordinate system, I'm going to split this up as a rectangle whose x component will move down the ramp in the speeding up direction and whose y component goes into the ramp. Imagine that weight is sinking you into the mud. In this new coordinate system, FGX and FGY add up to mg, but there's a funny change of coordinates here. Because of the rotation, that angle is now a vertical angle instead of a horizontal angle. That means FGY will actually go with cosine in this triangle, and FGX is going to go with sine. So let's talk about that, and we'll get you some equations to write down for your notes. The weight, Fg, is the same as it always has been, is the mass times the gravitational field. But when I split it into its x and y components, the x component is going to be responsible for accelerating the object down the ramp. The y component is going to be responsible for balancing against the normal force. Because the change of coordinates made it a vertical angle instead of a horizontal angle, FGY is actually going to be related to cosine and FGX will be related to sine. So let's see what that looks like. FGX is going to be the weight times the sine of the ramp angle. FGY is going to be the weight times the cosine of the ramp angle. If I substitute mg instead of weight, I can easily write FGX is mg sine theta, and FGY is mg cosine theta. So let's write down the red equation responsible for accelerating, and the blue equation responsible for canceling the normal force. And I'm just going to make that a little bit more clear that FGY goes with cosine. So remember, you won't have to memorize these equations, but what you will need to be able to do is know when to apply them. So when you write down these equations, write down what you'll use them for. You're going to use FGX to figure out how much force accelerates an object down a ramp and causes it to speed up. And you're going to use FGY equation to determine the normal force acting on an object. So if you're asked a question like this one, how much does a 50-kilogram person cause a scale to read? I'm thinking to myself, that's the normal force. So I'm going to use the FGY equation to determine that. FGY is going to be equal to the normal force. So that's mg cosine of 7 degrees. So I'm putting in 50 kilograms. G is 9.8, cosine 7 degrees. And this gets me a normal force of 486 newtons. Now, comparatively, a 50-kilogram person would have 490 newtons of weight. It's important to note that the normal force will always be smaller than the weight. The weight has to be larger than the normal force because this object is accelerating downward. Now, let's try. And the steeper this angle is, the more pronounced this effect. So now let's go calculate the acceleration. Because I'm finding the acceleration, I'm going to use FGX to calculate the force that pulls the person down the ramp. FGX is mg sine theta. That is 50 times 9.8 times sine of 7 degrees. But that doesn't directly get me the acceleration, right? This gets me the force. It gets me the force that pulls this person down the ramp. In this case, FGX is about 59 and change. Let's call that 60 newtons. So the net force, the only force causing acceleration, is going to be this approximately 60 Newton force. And if you remember Newton's second law, the net force would just be my 60 newtons divided by the 50 kilograms of mass, gets me 1.1 meters per second squared for the acceleration. So I'm going to use this last example to show us how acceleration doesn't depend on the mass of an object, even if that object is Santa. So let's say Santa is climbing this roof at 60 degrees, and it is unfortunately frictionless. The force that Santa is being pushed into the ramp, the force that would break through the roof of this poor person's house, is proportional to his weight. I would be taking mg cosine theta, taking my 140 kilograms of Santa mass times 9.8 times cosine 60, And this gets me a 686 Newton force that's trying to push Santa through the roof. Bad news bears. But it gets worse, because Santa's not going through the roof. There's only one force in the x direction, the red one, and that's your FGX, the mg sine theta thing. But notice that the mass cancels. In the x direction, your acceleration doesn't depend on mass. And we saw that in the lab. And when I plugged this into my calculator, bad news for Santa here. Santa is going goodbye. He's going to be accelerating down that ramp at 8.5 meters per second squared. Because this is an icy, frictionless, frigid roof, he's accelerating almost at the same acceleration due to gravity. 8.5 meters per second squared is a very large acceleration. So if I had to summarize this method, I would think to myself that our gravitational force is going to be broken up into components. The normal force is going to be perpendicular to my ramp and is going to be canceled by the y component of gravity, the one I've been drawing in blue, the FGY component. But I've been drawing the FGX component in red, and this component is going to be responsible for accelerating objects down a ramp. Because we rotated the coordinate system, x no longer only goes with cosine. In fact, you should write this down. For ramps and ramps only, FGX, the x component of gravity, will be associated with sine, and FGY will be associated with cosine. But you should be able to tell these apart because this should only occur on inclined planes. So let's go get you some practice. Best of luck!